Okay, so jumping back, there's just a couple last slides on the review of dislocations. And I really want to stress that this is meant to just be a review, right? I talked to Professor Ghazi Saidi, and she gave me sort of really detailed descriptions of what she covered, right? So I'm not, previous versions of this class, I did a lot of Kohler calculations. Right, and in those years, I had a fair number of mechanical engineering and ISC students who had never heard of a dislocation before, actually enrolling in the class. This year, we don't have that, so I decided let me just try and give a sort of a brief review, right? And just so I can point out what I think are going to be the key ideas that we'll use going forward. Right. So keeping that in mind, right, since it's just meant to be a review and it's not new material, this is probably not going to likely be very heavily represented on the exam, right? With the exception of the big key ideas that you're going to have to use. The first being that the energy of the dislocation is going to be GB squared, right? So the stored energy due to dislocations in a material is going to be proportional to the dislocation density, GB squared, right? Why? Where does this come into play? Right. This is one of my my big rules of thumb, right? So in candidacy exams, I like to talk about my material science rules of thumb, right? Which is my sort of off the top of my head toolbox that I use when I'm first presented with something, a situation to analyze, right? Square root ET is the first thing I go to whenever I have a diffusion problem, right? Anytime there's a dislocation problem, GB squared, right? Anytime I have an alloying thing, right? I look at the Hume-Rothery rules, right? Is this likely to be a solid solution? Am I likely to phase separate or form intermetallics? Right? These are the sorts of things that are really powerful, big ideas that if you sort of internalize them, you can begin to think rationally and do back of the envelope calculations for just about any problem that you're interested in. And most of the time, we don't care about exact numbers, right? We're interested in, are we going to recrystallize, right? Are we going to some other phenomenon? So where is this going to come up, right? Over and over again, right? So if the energy of a dislocation is dependent on the shear modulus of the Berger's vector, right? What if you have a nickel superalloy where you've got a dislocation that's a full dislocation in the gamma matrix, but a superpartial in the gamma prime? Shear modulus is different. So you've got a difference in energy across the length of your dislocation line, right? This is going to directly give rise to hardening behavior that we're going to see in the next topic, right? So these are sort of ideas that can be applied to concepts where they don't initially jump out at you. So two other ideas that are really critical when thinking about dislocations is, in terms of mechanical properties, is what's the driving force for slip, right? Remember, we have a dislocation line, and dislocation lines aren't normally perfectly long, straight segments. They're curved regions, right? We have some arbitrary stress field. Stress is our force density within our material, right? What direction is our force acting on this line? Right? Force is always going to be acting perpendicular to the line, right? That's the direction that we're going to be considered. So if we consider the work done in moving this dislocation in some distance, right? That's always perpendicular, right? We can take the derivative of our work with respect to our displacement, right? And so we have tau b, right? Well, tau, right? We want our, this is our shear stress. If we have a general stress, we want our traction vector on a, and our normal here is given by our Berger's vector. So that's our resolved shear stress, right? And this is just a special case of the Petrikohler equation. Right? What is the driving force? The key thing to remember is that our force always acts perpendicular to our dislocation line. The other key idea is line tension, right? Strain energy per unit length of dislocation, right? So this is the work that we have to do to increase dislocation length, right? So this is critical when we talk about the activation of a Frank Reed source, right? Or the thermal annihilation of dislocations by annealing, right? We're removing dislocation line length. Right? So there's always a line tension associated with that dislocation because there is a energy associated with additional curvature. Right? And that's going to be GB divided by the radius, proportional to GB by the radius. So the smaller your radius, the higher your degree of line tension. Right? Why is that important? When we talk about hardening, we're going to be talking about dislocations moving around particles, right? Or having enough tension to go through them. Okay. Also, critical implication of GB squared is the dissociation into partials. I'm not going to be so worried about specific dislocation reactions for this course, at least, but we have to remember that in an actual material, we never see a perfect screw segment, a perfect line segment, right? We always see, right? It's always much messier, right? We always observe dislocations in other states, and in FCC, if our stacking fault energy is low enough, we typically always see dislocations dissociated into partials. And the implication of this is pretty important for mechanical behavior. It's a little hard to see on the projection, but the stacking fault energy controls how likely you are to find partials that are a significant distance away from each other, right? And so that means it's going to control the slip behavior, right? If I have a screw dislocation, I can cross slip. If it dissociates into partials, now those screw components, now have edge character. I can't cross slip. I need to drive those partials back together before I can cross slip. So if my stacking fault energy is very high, my partials don't separate. They can easily come back together, and I can cross slip around obstacles, right? So that means I see slip traces in my material that are wavy. My dislocations are easy to move around the obstacles that they encounter. If I have a very low stacking fault energy, my partials are widely separated, right? Other things get in the way. The probability of them coming back together to form a perfect screw again is very small. So I have very straight planar slip. I don't go around obstacles, right? So what does that mean? I have very different strain hardening behavior, right? We'll talk more about how dislocations can be obstacles to other dislocations and strengthen your material. Well, if I have a way of getting around obstacles, I have a very low degree of work hardening or strain hardening. Where if I can't get around obstacles, I have a very high rate of work hardening and strain hardening. And we'll talk about that in great detail after the midterm. Okay, the last idea is how dislocations move, right? They don't move, the entire line does not take one big step forward, right? They don't simultaneously move the entire line at once. Instead, we tend to move in a step-like fashion, right? The stress, the driving force is high enough here, but not quite high enough out here, so we move this portion of the line forward in a burst, right? Leaving behind a kink, right? And these kinks will move up in segments. Right now, kinks are distinct from jogs. We talked about jogs earlier. Jogs are out of the plane. Kinks are in the slip plane, right? So basically, just think of our driving force for slip is higher than our Pyrrhus barrier here, so we move this little region forward. The energy penalty is now we've got a radius, right? So we have to overcome not only the Pyrrhus barrier, but the line tension associated with the formation of the kink. Right. And so the line tension and the Pyrrhus barrier has to do with our dislocation width. And so if we're in less close packed structures, our core widths are such that we get these narrow, more difficult to move kinks. But if we're in easy to move structures with low Pyrrhus barriers, we tend to have more diffuse kinks. Right? They don't look like the line tension is significantly smaller here, right? Because of the difference in the balance between the Pyrrhus stress and the line tension. And again, this is not something I expect you to be quantitative about, right? If this were the structure and defects course, right, then we would do that. This, I just sort of want you to sort of remember trends and think about how this comes into play when we talk about dislocation interactions with respect to macroscopic mechanical properties, right? And so we form a kink, and then this region grows will tend to grow by lateral velocity, right, as we step forward, right? This means we're moving a small section of our dislocation. It's a way of moving a small section of our dislocation forward without creating new regions of high curvature, right? So it's sort of the motion that keeps our activation energy low. Right? You can imagine if we tried to move another segment up here, now we're creating a double kink, right? So we have increased line length. Okay, so that's the dislocations in a nutshell. I'll post let's see. Okay, So now we get to what I think is the exciting stuff, because it's my research area. Right? So, if you think about the problem of understanding the plasticity of metals, right, or ceramics at elevated temperatures, it's conceptually a difficult problem, right? That a lot of people don't immediately intuit. You ever play the game pick up sticks as a kid, right? You got a big bundle of sticks and you dump them on the ground, right? And try and understand what happens to this whole big pile if you move one stick. Now imagine each of those sticks has like 48 degrees of freedom in which you can move it. And you're trying to understand how one stick on the bottom of the pile is going to move if you push a little bit on this one up here. That's sort of an analogy as to what's going on. You've got this heterogeneous mix of crystals, right? At the time, we had no good way of characterizing them, right? A lot of this work was done in Sachs and Towers was done in the 20s and 30s, right? We just sort of realized that metals were crystals, right? People still didn't believe in dislocations. But somehow, the classical mechanics people, starting from ideas of composites, were able to look at and say, well, what has to happen if we're going to make a deformation that's either satisfies stress equilibrium or satisfies compatibility? There's some really deep things in here that I wish we had sort of a little beyond the scope, right? If you think about it, it's not immediately intuitive that the stress field in a highly heterogeneous medium like a polycrystal is unique for a set of boundary conditions. Are there multiple stress fields that could potentially satisfy equilibrium? It turns out no. It turns out that is unique, but that was not a trivial problem to solve, right? And whether or not your stress field in a body is unique is going to greatly determine what happens as you evolve. So we need to start, before we can think about the polycrystal problem, we need to go back to single crystals. So if we think about what happens to a single crystal during deformation, we tend to show three stages of behavior, right? So the first, if we have, here's shear stress versus shear strain of a single crystal. So we're shearing this along a well-defined slip plane. We get a region of elastic followed by a plastic deformation of what we call easy glide, where there's no increase in the stress. Then we enter what's known as stage 2 hardening, which is we have a nearly constant hardening rate, which is for the most part independent of strain rate to temperature. And then into stage 3 hardening, where we have a decreasing rate, where we approach an asymptotic stress value. And this is very dependent on the rate at which we're deforming our material and the temperature at which we're deforming it, right? And this represents a balance where we're striking a balance between recovery and work hardening, right? We think of work hardening as the development of dislocation structure and dislocation interactions, right? The recovery is the removal, annihilation of dislocations. And when we reach our asymptotic stress value, it means that our dislocation generation and removal rates are balanced and equal. Okay? we're going to talk about hardening later. So for the most part here, we're going to be talking about stage 1 initially. We know we talked about the resolved shear stress, right? So if we actually take a single crystal and put it in compression, right, we see clear lines, right? Those are basically slip. Right? It's not a theoretical exercise. If you do a single crystal compression, you actually get what is shown in the textbook, right? So we have our Schmidt rule, right, which is the projection of the force onto the slip plane normal and the Berger's vector direction, or slip direction, right? If we want to generalize that, we can create a Schmidt tensor, right, which is just the outer product of our normal and our slip plane, right? This is generally a non-symmetric tensor, and it's hard to see, right? But just the contraction of our stress tensor with our Schmidt tensor gives us our resolved shear stress, right? So this is independent, right? So this can be pre-calculated for the crystal geometry, right? And then whatever our stress state is gives us the resolved shear stress on that slip system.
Were those two dots named the operator?
This is the double contraction, right? So that means you're summing over I and J, right? It's the generalization of a dot product to higher, right? You're just putting all the terms together and then some. Okay, so crystallography of slip. We know that in FCC we're for the most part on the 111 planes in the 101 directions, right? So we've got 3 slip directions per plane. How many 111 planes are in the family? 8. You've got positive and negative, right? So 4, right? So 4 times 3 gives us 12 FCC slip systems. If we consider that slip in both directions, that gives us 24 possible ways we can slip in a FCC crystal. All of the slip systems are degenerate, right? They're all the same directions, in the same plane. So the energy to activate them is going to be the same. BCC, that's not the case, right? The slip direction in BCC is always going to be in the 111 direction, but we have multiple planes that contain 111, right? And the activation energy for each of these, right? The geometry is not all that different. The Berger's vectors aren't all that different, right? So we have 48 possible slip systems in BCC. If we consider the directionality, that gives us 96. G.I. Taylor coined the term pencil glide for BCC, which is really interesting because he thought about it as we always are going to slip along the 111 direction, but we have so many planes available that the plane really doesn't matter, right? So think about taking a box of pencils and making them into a bundle. That's your 111 direction, right? And you can move them up or down. You can shear them in any which way you want, right? And he called that pencil glide, and that name stuck. So when people talk about slip in BCC, they often refer to pencil glide, meaning that we're activating multiple slip systems simultaneously. So which do you think is going to have a greater temperature dependence, FCC or BCC? FCC, I'm on the slip plane in the slip direction, right? So I'm always on the closed path plane in the closed path direction. BCC, I'm in a closed path direction, but none of these planes are closed path, right? So in general, these are going to be more difficult to activate, and they're going to have a higher degree of temperature. Right? Thermal energy is going to help you more here. HCP is a very different story. We've got we have a closed path basal plane, right? And our closed path direction is the 1,1 bar 2.0 type directions, right? And so, our basal slip, right? And our prismatic slip, our slip plane is the prism plane, right? Both of these are very easy, depending on one can be easier than the other, depending on which one you're in. But notice, what's the Schmidt factor for compression along the C-axis for both of these systems? It's identically 0. So that means if we're going to deform by slip in a hexagonal metal, we need to activate other slip systems, right? We can activate the 1,1 bar 2.0 in a pyramidal slip system, right? This is a pyramidal, right? Or we can activate other slip directions, right? 1,1 bar 2.3 directions on these planes, and we call this C plus A pyramidal slip, right? Much more difficult to activate than either of these, right? Okay, what do you do? I have that slide, or did I take that out? Yeah. Okay. So, what do you think is going to be the primary driver between whether basal or prismatic slip is going to be easier? Right. Well, in many systems, basal is easier, but in some other systems, prismatic is easier.
C over A ratio?
C over A ratio, right? Depending on your C over A ratio. So, group 4 metals, titanium, zirconium, hafnium, tend to favor prismatic, right? So slip in titanium is primarily prismatic, whereas magnesium is going to favor basal, right? And so I'll leave it to you guys to work out what the C over A ratios of those are and come up with the trend, right? It's a sort of a good visualization of crystal geometry if you can rationalize why prismatic is favored in titanium and versus basal and magnesium. So Schmidt law. So Schmidt speculated that in single crystals, right, that the yield stress varied from sample to sample. Initially, people knew they knew how to grow single crystals, but before X-ray diffraction, they didn't know what the orientation of the crystals were. So they just basically said, I'm testing these crystals and I'm getting very different yield strengths for all these different samples. And that's where Schmidt came in and came up with the famous law that you learned in your first year as an undergrad in materials. Right? So it's all about the critical resolved shear stress. Right? The stress resolved on the slip plane normal in the slip plane direction. In the slip direction, right? And once that reaches some critical value, you're going to overcome. What goes into that critical value, right? The chiral stress, right? So an intrinsic value and how much work or other strengthening you have in there, right? It could be alloying, it could be other dislocation content, right? So the critically resolved shear stress isn't some static value, right? That's going to evolve with time and processing and composition and all these others. So if we think about dynamically what's going to happen, right? If I have a single crystal and I pull on it, I shear on this plane, I now have a bending moment, right? If my ends are free, right, my sample is going to rotate, right? And my slip direction is going to rotate towards my tensile axis, right? So under tension, the slip direction rotates towards the tensile axis. In a real test, this is constrained, right? So what I end up with is differential slip from the top to the bottom of my sample, and I get lattice curvature, and the effect is still the same. Right? At the center of my sample, my slip plane, my slip direction rotates towards my tensile axis. In compression, just the opposite happens, right? My slip plane normal rotates towards my tensile axis. Right? I'm going the opposite direction. Right? Okay, so general trends. So if we just think about FCC, we have to think about the geometry and the crystallography. How do we decide what slip system is going to be active? Right? We can calculate the Schmidt law, the Schmidt factor for each of them. Right? That's sort of the long brute force way of doing it. FCC has this nice little trick. You can pick it up from the stereographic projection, stereographic triangle. Right? If we think about where on our stereographic triangle our forces, our resolved shear stress, what crystallographic direction is acting on. Right? Let's say it's acting in this triangle. We project over the 100, 110 line to find the nearest 111 plane. Right? And we come over here and project over the 100, 111 line to find our slip direction. Right? Why does this work? Right? What's the highest possible Schmidt factor? Right? When everything's 45 degrees apart. Right? These planes are 90 degrees. So if we follow 45 degrees along the great circle between them, we land smack in this triangle. Right? So it's just a visualization of our crystal geometry. Right? And so from the stereographic projection, we can get a couple other slip systems. Right? So the conjugate is the slip system that would activate if you had the force in here. We'll see this because as our crystal rotates, right, we end up moving along this line where we activate both. At our stable orientation, we're activating both this slip system and this slip system simultaneously. So that's why we call it the conjugate system. We also have the coplanar, right, down here. This will activate, this is the force, the loading direction that will activate a different slip direction on the same slip plane. Right. So this just shows the geometry that I talked about before, but we can look in the stereographic triangle and plot the Schmidt factor, the highest Schmidt factor for everything, right? And notice what do you see, right? We come down, our maximum is 0.5, our minimum value is 0.28, right when we are on the 111 direction. So 111 is our plastically hard direction. Right? But basically, most of the stereographic triangle has, right, we got 24 equivalent slip systems, right? So our Schmidt factors are pretty high, right? It's not it's anisotropic by a factor of 2, right? We don't have a factor of 10 difference between how hard different grains are to activate in FCC, right? In HCP, you might have a really huge factor because of the energetic differences between the slip systems. But in FCC, when everything is the same, basically our plastic anisotropy is about a factor of 2. Okay. So if we think about what happens to orientation, right, lattice reorientation under tension, right? If we're here, we basically under tension move up to the 100,111, right? And then we move along this to the 211 orientation. That becomes our stable orientation, right? So in reality, we come up here, we move it. It's never perfect. There's always overshoots here, so the zigzagging along this line. Right. And so again, the 211 orientation isn't in and of itself important for this class. What is important to realize is that if I have a single crystal and I perform it in isolation, I'm going to go to some stable orientation, right? This is the development of texture, right? During mechanical processing, you have the development of preferential orientations that appear, right? And so anytime you deform a sample, you're destroying the uniform randomness, right? And as you develop preferential orientations, you're changing the anisotropy of your sample. Those are the key ideas to get in, right? I really don't care that it's the 211 orientation, right? It's the idea that by mechanically processing a crystal, you are changing the overall macroscopic properties by developing anisotropy. Right? Under tension, under compression, we come down to this line and we all filter out into the 110. BCC, things start to get ugly, right? Because we have a lot more possible slip systems, right? Depending on where you are in the stereographic triangle, you're going to have different systems that are active. So you don't have a nice trick, right? You have to go through and calculate them all, right? And notice, if we think about this notion of pencil glide, right? Instead of being contours, right, now we have these sort of lines where we have similar Schmidt factors, right? So if you're preferentially oriented, if your deformation direction is well aligned with your cube orientation, you're going to activate 1. If you are 111 or 110, you're going to activate a different slip system. Right? But the patterns, right? So if you're here under tension, we rotate and we end up at our 110 stable orientation, right? And if we're under compression, depending on where you start out, you end up either 100 or 111. Again, what the stable orientation is not critical. It's the concept of that by deforming, we're altering the orientations, we're altering the anisotropy. Right? So how do we solve Schmidt problems? What we need to do is define the orientation of our crystal. So I added a bunch of supplemental slides that talk about different ways of defining the orientation of the crystal. But anyway, for the most part, the orientation of the crystal, this orientation matrix, it's a transformation between your deformation coordinate frame and your local crystallographic coordinate frame. right? And so we can transform a vector in our sample frame to one in our crystal frame by our orientation matrix, right? So that means we can transform our stress in the sample frame to our stress in the crystal frame by the operation of our orientation as well. So we need to always put everything into our crystal reference frame because that's how we define our geometry, right? So whenever we're solving problems with crystals, we have to either transform our loads to the crystal frame or our directions to the sample frame. You just have to be consistent about it. But then you just take all your Schmidt tensors, right? Project them by the stress, and whichever one's the highest is going to be the operator. Resolve shear stress. Right? Remember, you have to consider negatives, so it's highest in value, not highest in absolute value, not highest in sign. Sign just tells you which way you're going to go. Right? So in FCC, you do it over your 12, and BCC, you do it over your 48. Right? In reality, the classic Schmidt law predicts one active slip system, right? And nothing happens until it's activated, and then all of a sudden you have plasticity. So that gives you a perfectly sharp elastic plastic transition, right? That's never actually observed, right? In reality, the elastic plastic transition is this curved region, and that's why we have this concept of the offset stress to define our yield. So and also this transition becomes higher or lower based on the loading rate, or rate dependent. We have a rate dependency. So the classic model for this becomes a power law, right? And this is what underpins the heart of every crystal plasticity model that's sort of out there, an equation, not necessarily exactly this, but something similar, right? So here is our Schmidt tensor times our stress. So this is our resolved shear stress on slip system S. This is the critically resolved shear stress for slip system S. This is a very large exponent, say 50 or 100, right? So if this is slightly less than 1, right, take a fraction that's slightly less than 1 and raise it to the 50th power. What happens to it? It becomes very, very small, right? What happens if this is slightly higher than 1? It becomes very, very large, right? So that gives us our shear rate. Our total strain rate gives us is defined by the shear rate, the sum of the shear rates over all of our slip systems that are active. So typically this is given, we give a set of boundary conditions, right? We give it the strain rate that we're applying. So we're looking for the stress that makes all of these to be either 0 or 1, right? So that we deform at the right shear rates on each slip system to get our, right? This is a very stiff nonlinear set of equations, right? Because of this very high exponent here, right? You have to be dead on to get a root, to find your root. And that's where the numeric difficulty of all these models fall into. Right? But the general idea is the more rate sensitive this is, the higher this exponent is going to be. And the higher this exponent is, the sharper our transition here. right? If this becomes infinitely high, it only has value when this is exactly 1. If this is a little lower, you end up with a rate that still only has value near the correct stress, but it takes a range of values, and that gives you the rounding of your elastic plastic transition. Okay. And then I think the last topic for today is how do we estimate what the critically resolved shear stress is? Now, I want to make a really important observation, is that we cannot predict a yield stress, right? This is like a huge open challenge. We do not have the ability to actually predict what the yield strength of a metal is going to be from first principles, right? We understand how individual dislocations move, right? We don't understand how large populations of dislocations collectively behave, right? And how large populations of dislocations collectively self-organize to form structure, right? So in very limited cases, we can make a reasonable estimate, like if we're doing, say, very high rates on very, very small samples, right? But we can't predict the quasi-static yield strength of the pulp. Right? Cottrell actually made the observation that he said in the preface to his book that physicists always talk about turbulent flow as being the most difficult unsolved problem in physics. And he said yield and work hardening in metals is orders of magnitude more difficult. But we can make some sort of assumptions. For the most part, in engineering metals, right, the strength of material is going to be directly controlled by the density of defects, dislocations, right, second phase particles, and internal interfaces. Anything that the dislocations can interact with, right? If our primary mode is dislocation slip, any obstacle to the motion of dislocations is going to increase our strength or increase our critically resolved shear stress. Right? At stresses below the critically resolved shear stress, dislocations are only traveling the short distances between obstacles. Right? It has to overcome one obstacle and then move to the other. Right? You can think sort of conceptually that above the critically resolved shear stress, we sort of have enough driving force to push past these obstacles at some regular rate. Right? So all of our obstacles aren't going to have the same degree of pinning force. There's going to be some distribution, right? There's statistics in here. But we're going to make the argument that it's going to be approximately proportional to the critical resolved shear stress is going to be approximately proportional to the square root of the dislocation density.
What does that M mean?
It's a constant. It's called the Taylor factor. It accounts for the orientation of the grains in a polycrystal. And we'll define the Taylor factor later. But that the critically resolved shear stress is going to be proportional to the dislocation density. Right? And we can sort of get from there by thinking of a Frank Reed source, right? The activation. of a Frankfurt source. So we have here two ends of the dislocation, right, that are pinned in place. Typically, we think of these as being pinned in place by jogs, so the rest of this dislocation line is either in a plane above or below this. So we have plenty of area without our dislocations running into each other, right? And basically, if we have a force here, if this is immovable, our dislocation line will blow out between our pinned endpoints, right? And eventually will just become larger and larger and larger, circle back around and meet itself, in which case these two segments have opposite sign. So you have annihilation in the middle here. So that gives us a line and a loop. This loop is then free to go out into the plane. So this is our simplest dislocation source. Right? There's a whole bunch of other potentials, but okay. So we have to think about how much force do we need to actually activate this, right? This is another great candidacy exam question. Right. So our line tension is going to be proportional to GB squared, right? We care about the force of this resolved in the vertical direction. And we said the driving force for slip is going to be tau b, the force exerted on the dislocation per unit length. And so the total force on the pinned dislocation is the length between these two, right? The longer the length, the more force we have acting on the total dislocation, right? We integrate over this entire length, right? So that's given by gamma tau b, and our force between our line tension and our driving force have to balance, right? So pretty simple analysis. All right, and we end up with tau depends on the cosine of this angle phi, GB divided by the distance here, right? Hopefully everyone's seen that analysis before, but it's a fairly straightforward force balance, right? So if we think about what happens, the shear stress is going to be proportional to the radius of curvature, right? And if you work it out, the amount of force required is roughly the same for 1 and 3, right? Because here, because of our angle versus the line tension, right? But we go through a maximum at 2, right? This is where we have the smallest radius of curvature, right? And so our maximum stress is going to appear at GB divided by this separation when our phi angle goes to 0. Right? Again, it's just the force balance, right? We go back to this equation, right? When this cosine goes between 0 and 1, so we want our cosine to be 1. Right? That happens when our angle is 0. Okay. So dislocations that are stuck between these immovable pinning obstacles, right, are only going to move short distances if the stress is less than the bowing stress, right? Once the stress rises above this value, then we can bow around the obstacles, right? This is ignoring cutting for right now. Situations where cutting is easier. But right now, if we just consider bowing, Right, we need to get above the critical OR1 bowing stress. Right. So if we think about now this in terms of dislocation densities, right? So dislocation, oh shoot, we're sort of out of time. Dislocation density is line length per unit volume. So we'll pick this back up on Monday, and we'll see how far we get. And that will be our sort of exam cutoff. Will be the end of lecture on Monday. Right. So basically, where we're going is we're going to get the dislocation density, and then do some stereology with distances to get our relation of how critically resolved shear stress is really related to the square root of dislocation.